Welcome back to our lecture series. Today, in this lecture, that is lecture 3, we expand our understanding of optical absorption by introducing an important concept, that is quasi-particles. We will begin specifically with excitons. Up to now, we have described excitation as an electron leaving the valence band and moving independently into the conduction band. This picture is useful, but it is not always complete. In many real materials, especially at low temperatures or in materials with low dielectric constants, the physical situation becomes more subtle. When an electron is excited into the conduction band, it leaves behind a vacancy in the valence band. This vacancy behaves as a positively charged particle called hole. Now notice something important. The electron carries negative charge and the hole carries positive charge. Because of this, they experience Coulomb attraction. Under suitable conditions, the electron and hole do not immediately separate. Instead, they remain bound together and orbit one another. We define an exciton as a bound state of an electron and a hole formed through Coulomb attraction. You may visualize an exciton as similar to a hydrogen atom, but instead of a proton and an electron, we now have a hole and an electron interacting inside the dielectric environment of a crystal lattice. This concept is extremely important because excitons modify how materials absorb light. Let us now examine how excitons appear in an energy band diagram. We begin with the valence band having effective mass mh and the conduction band with effective mass me. The energy difference between these two bands is the band gap energy denoted as Eg. If electrons and holes were completely free, absorption would occur exactly at this band gap energy. However, excitons change this picture. Because the electron and hole are bound together, their total energy becomes slightly lower than that of free carriers. As a result, new discrete energy levels appear just below the conduction band minimum. These are called exciton energy levels. Now consider what happens during UV visible absorption spectroscopy. Instead of observing a simple sharp edge at the band gap energy, we observe sharp absorption peaks. These absorption peaks occur at energies slightly lower than Eg because energy is required not only for excitation but also to overcome the exciton binding energy. By analyzing these peaks, we can calculate the exciton binding energy and the dielectric properties of the semiconductor material. Thus, excitons provide deep insight into material physics through spectroscopy. To fully understand optical transitions, especially indirect transitions, which we will study next, we must introduce another key concept, that is the phonon. A crystal lattice is not perfectly rigid. Atoms continuously oscillate around their equilibrium positions. These vibrations occur naturally due to thermal energy. In physics, we quantize these vibrations to describe them properly. A phonon is defined as the quantum of lattice vibration in crystalline solid. This idea is analogous to photons, just as light energy is quantized into photons. Mechanical vibrations are quantized into phonons. Phonons carry energy and momentum through the crystal lattice. This becomes crucial during certain optical transitions. Sometimes a photon alone cannot satisfy momentum conservation. In such cases, the crystal lattice must assist by absorbing or emitting a photon. This interaction between electrons, photons, and phonons is a fundamental to understanding indirect bandgap materials. In today's lecture, we introduced exciton formation, exciton energy levels, and the concept of phonon. These ideas prepare us to understand the difference between direct and indirect bandgap semiconductors in the next lecture. Thank you.